So welcome again. Yesterday we talked about basics of neural networks. So today we are going to a little bit deep about recent advances or deep learning. The first part will be about the unsupervised learning. Actually, this part is very exciting because it can allow you eventually don't rely on that kind of big data. You can have small data. You can still learn something very useful. A second part is a case study of a HPC algorithm that can make the deep learning system scalable. And the third part is about some new deep learning model architectures. You know, we want models to go deeper, and so there are some problems, and these are two new models I'm going to introduce. And last part is about model compression. So imagine you want to port this big neural network trained to your mobile phone. It's impossible because it is like several hundred megabytes, and you want to compress the network such that you can put it on device, on your any portable device, then for your own learning purposes. So when it comes to unsupervised learning, basically it means you are exploring the data that without ground truth, and this is exciting because the current deep learning is a luxury. By luxury, I mean if you want to do any intuitive task, you basically do not find that kind of labeled data. You need to, for example, Baidu or Google, they usually hire people to label the data by them with experts, for example, in the medical images. And for other images, you hire some people to label by hand. And this is unscalable when you want to do your own tasks where there's no data. So another concept before we dive into this cool network is called a generative model, which means you want your model to be generative such that you fit some model into this data sample from distribution, and this model can generate new data based on the model you achieved. So the ideal case in this unsupervised learning setting is you want to generate pictures that are fundamentally or at least not that similar from the training example. You are given some example like this, you want to generate more data. So you don't need that kind of big data. So this is the ideal case, and people are working towards that. So these cool networks called generative adversarial. The idea is that you have a generator which given some vectors from a Gaussian distribution, you want to sample this vector and generate an image. Some image like this, like we call fake image. And then you want to train a discriminator that can distinguish the generated image and the real images. So this is a competition between a generator and discriminator. The generator wants to fool the discriminator as much as it can, because we want eventually the generator can generate images that can confuse the discriminator search, and the discriminator can work really well, but it still got confused. So then we can use the image generated by the generator for our own purposes. And it's like a human cannot distinguish between the real images and the image generated by the generator. So these are the early paper published in 2015, the early results. So these four figures are for a different training data set. For example, the first one, the handwritten digital recognition task, where these red columns are those generated images that are most similar to those training examples. They are not exactly the same, they are different. But here you can see the resolution is not the high at that stage, so it's very low resolution. That's why it looks like blurry. But you have some learned like object faces, and this is very promising. But it has many problems and any other neural networks. For example, it's hard to train because it has a gradient problem. As you imagine, you want to optimize the generator and the discriminator. If you optimize like bias towards the discriminator, the discriminator did extremely well, then your generator basically have zero gradient. And also there's some other problem, like the generative example is not diverse. For example, some of them are very similar to the training examples. This is not very useful because this can easily lead to overfitting. And also, we want a loss function to be indicative to guide us through the training. We want the lower the loss, the better the performance of this generator and discriminator. But actually, this is not the case in the early version of this generative adversarial nets. And recently, there's a new GAN which is called Wasserstein GAN. So this is really neat work because it's through mathematics, it analyzes why the traditional GANs doesn't perform well, why it's not stable, because it's minimizing something else and is contradictive. So it introduced another concept called Wasserstein distance. The PR is the probability distribution of the real images, and this is the generator distribution. And then you want to take the lower bound of the expected absolute difference between the data, the two data points, where the two data points are sampled from the joint distribution of the raw images and the general images. So you want to minimize the distance, the expectation of the distance of these two images. And think another way, this is also called the Earth mover. Think another way, X is some sand or rock. You want to move to the place of Y. This function tells you that you want to do the minimum work for moving this X to the Y. And the nice property of it is differentiable. Training is unstable or have some vanish gradient problem because the gradient is not smooth previously. Now it becomes smooth, and also it is indicative. These are two different model architectures, but works the Y at the same Wasserstein distance. And you can see as you go over with the training, the general images become better and better. And this is really exciting because from the model architecture point of view, it just did a minor modification. But from the mathematical point of view, it's introduced some cool mathematical analysis, because for a long time, deep learning is being called a black box, and you just trained and it works. But there's some mathematical neat analysis going on there. If you're interested, I encourage you to look at the paper. So immediately, what this kind of adversarial network can do for us. So immediately people can do, for example, yesterday we introduced this semantic segmentation task, where you want to segment these images out. So now if you have very limited image, what can you do? So you can train a segmenter and the adversarial network together. So the input here for this adversarial network is not this image, it's the combination of the image with the output of its own prediction, or the image with the ground truth. So essentially, you want your network cannot distinguish whether this is come from your prediction or your ground truth. So you want the segment as close as possible to the ground truth. And it shows data performance on some data set. So this is really interesting, really hot topic, because this can be potentially applied to many other tasks, especially when you have very limited data. You don't need that much of computational power, unfortunately. For the second topic is a case study of of algorithm that can allows you to have constant communication time on a big GPU clusters for the synchronous keys. So we don't talk about the asynchronous keys because it's hard to debug from our engineer point of view, and it's sometimes it has suboptimal results. So this example is from Baidu's recent work on ring AllReduce algorithm, where this is this is a illustration of why we need to have that algorithm. So imagine you have four GPUs. In the synchronous key, each GPU need to send its gradient and receive its gradient. So imagine the network has 300 million parameters, which takes 1.2 gigabyte of memory, and if the bandwidth 1 gigabyte per second takes, if you have 2 GPUs, it takes 1.2 seconds for latency. If you 10 GPUs, you take another 9 multiplied by 1.2 seconds. So you can argue that this latency can be covered covered by doing a parallel concurrency. But if you want to have 100 GPUs, it's become impractical. So basically the ring AllReduce network work as this. Imagine you have an architecture like 5 GPUs where each one will send to its right neighbors and receive the gradients from left neighbors. And for the simple task of sum up all the numbers in an array, there are different chunks inside each GPU, and you want to sum all them up. So what you do is you send one chunk of data to its neighbor at each step, and then at this stage, the G1 will send all this result to GPU2, and so on. So basically, after 5 steps, each GPU will have have a total sum of partial of the data. So this is called scatter reduce, and then you are doing this all together. This also takes 5 steps to send the result, propagate the result to every GPU. So it turns out the communication cost doesn't depend on n. It's constant. It's basically limited by the slowest connection between adjacent GPUs. And when it comes to backpropagation, remember we are doing backpropagation in real training. You can and backpropagation can doing layer-wise, and this algorithm, because you can start on partial of the data, so you can do AllReduce on the layers, then already have the gradients, while waiting at the same time the other layers, we're doing the gradient calculation. So this even can make it much faster. So this scaling plot is for 5 nodes with 8 GPU each. It's a big network with 300 million parameters. So basically, when it comes to 40 GPUs, that you can see the number of examples you can process basically linear. So next topic is about new deep learning architectures. So people want to have deep network going very deep, as we talked about before. So, but it has problems, training problems. It doesn't optimize very well when it goes deep. So the first network I'm going to introduce is called Harvey network. Is invented by also the lab here in Manu, is easier, by the same lab. So the idea is, instead of doing this traditional computation where the output is activation of the X input and the W, which is the weight matrix, you add an additional weight term. We call it gate, a transformation gate and the carry gate. So this is the same idea like in the yesterday we talked about STM keys to avoid the gradient vanish problem in the recurrent neural network training keys. So the good property of it is when C is 1 minus T is if T is 0, then your output is completely the input. If T is 1, you have the original network. So combining these two, if you think as it's not a constant, but if you think as a constant, combining two, you have something between your initial input and your something you learned. So this allows the network to go in very deep, while, see, the green curve, the heavy network, and the error, the lower the better. So the heavy network can achieve much lower errors when the depths go to even 100. So actually the margin is very big. So the second, the first work is very general. The second work is actually a special case of this heavy network. So the motivation is also similar. They want to design a network which goes deep, and the observation is like this: when you go deeper, your 56-layer network have a higher error than those 20-layer network, and at that time people are thinking that it's not necessary going deeper the better. So people are doing designing some network blocks like this, which is called a residual block. So the idea is similar as heavy network. Instead of you going sequentially in this layer, you have some chain here where the input for this layer is not just this layer, but also the input here. So as you can see, this is very similar to the heavy network special keys, and you can do very deep modeling like this. You can go to more than hundreds layers. So these are the comparison with the plain network and the residual network on different layers. So the bold curve is the validation error. So as you can see, this on this residual nets, the 34-layer residual network is substantially has substantially less error than the plain version. So it's the winner champion of this ImageNet competition 2015. The top 5 errors is smaller, much smaller than the GoogleNet or the VGG network. So the last part is about model compression. As I already mentioned, this is very important, especially when you want to apply deep learning for your own purpose for mobile devices. You need to have a network to be smaller, but also keep the performance as much as possible. So the idea comes, the network is over-parameterized. You don't need that 300 million network to achieve this performance. So the first, this work is called SqueezeNet. It's also this convolutional neural network. If you remember doing convolution pooling, it's just doing some minimization of this number of weights. For example, you have 3x3 filters, which have 9 weights, but you can reduce to 1x1 filters. Also, you can decrease the number of channels. We will talk it here. So basically, you have this kind of module where traditionally, we usually have like 32 or 46 filters, but you can have this kind of less filters combination with 1x1 filter with 3x3 filter. So you only have 4 and 8 filter totally. So the overall architecture like this. So each module includes then 2 parts. So you have convolution and pooling, and the performance is amazing. So if you look at AlexNet baseline, is the size is 240 megabytes, and the top 5 performance is 80%. But if you use the SqueezeNet, which can do 50 times reduction, keep the accuracy the same. And if you do a deep compression, which I'm going to talk in the next slide, you can even achieve much higher reduction. So the idea of compression is based on, it's not about the SqueezeNet where you play with this kind of architecture. It's about playing, for example, here you're going to prune unnecessary connections. For example, some connections have a weight that's smaller than a certain threshold, you are going to throw it away. And this achieve about 10 times reduction. Then you are going to cluster the weights, quantize. You're going to cluster the weights into several groups and use that groups as a representation for that floating point number originally in the weight matrix. And then you do this Huffman coding, which will further compress it. So the idea of quantization is like you have 4x4 matrix, which correspond to 4 input neuron, 4 output. So you have some numbers. Each color indicates this number belong to one cluster. For example, these numbers belong to the cluster, this one, which are near 2. So also you have these gradients, and you group by them with different bins. And what you do at last, you use these numbers and minus this learning rate, multiply this gradient as your rough representation. So the next part is Huffman coding, which I guess you probably know about this. Use the most frequent occurred version. Use less bits to represent that, because initially we have 34 bits for representing a floating point number, and you can reduce it to 6 or 8 bits. So this saves another 20 to 30% storage. So that's all. And any questions? So for the first part is really the recent 2 years work, the unsupervised learning. So there's lots of ongoing open questions, and you feel free to discuss.